back. This is Unit 3.3, and this is our section on light. This is Chapter 5, specifically page 146 in that chapter. It's 146 to the end of the chapter. Okay, so Bohr, we talked about Bohr when we talked about the planetary model of the atom. Bohr knew that passing high voltage electricity across two electrodes through a sealed glass tube that contained the hydrogen gas inside of it caused this gas to emit light. And he used what's called a spectroscope to break down this light into its different wavelength components or colors. And this can be accomplished also with a prism, which is a triangular shaped piece of glass and light from the sun. So right here, you see that when we take a prism and white light that comes from the sun, it breaks it down into all of the different wavelengths. So it contains every wavelength from about 400 to about 700 in those ranges. And this is what's called the continuous spectrum because it's continuous light. But just hydrogen alone, when you look at it through a prism, breaks down into only 4 wavelengths. And these wavelengths at these particular colors, 656.1 nanometers, 486, 433.9, and 410.1. You only see those 4 colors. Okay, so when Bohr looked at this, he came up with 4 postulates or 4 truths. That's what a postulate is about this. 3. And he said that the hydrogen atom only had certain allowed energy levels or stationary states. So that means that here that there are stationary states. So here the green part is the nucleus, and then here's one stationary state, here's one, and then this one out here is one. And that each of these states corresponds to a circular orbit of fixed size. Okay, that's around the nucleus. The larger the allowed orbit, the greater energy that's associated with it. So we talked about this when we talked about the d electrons. So, this has high energy out here orbiting around the nucleus. And then if we lose the energy, like the d electrons are less energy, then they don't sit directly on this, they're somewhere below. Okay, and then here's the second energy, and then if it loses more, then here's the first energy. Okay, so as you go down, it's low energy, and as you go up, it's high energy. And no other orbits existed in the atom. So each allowed energy state was given an integer number, n equals 1, n equals 2, and n equals 3. And Bohr called these the quantum number. Okay, and the lowest or the smallest orbit corresponds to the lowest energy, and this is called the ground state, where that electron normally exists. It's called the ground state, and that's designated as n equals 1. And then the larger orbits have greater energy, and they're designated again 2 and 3. Okay, and these were called excited states. Now this is only for hydrogen. Okay, for hydrogen. So the ground state for hydrogen is n equals 1 because it only has that one electron, and it's on the orbital closest to the nucleus. Okay, so if it gains energy, it's called an excited state, and the electron can bump up to this orbital or this orbital. And then ground state is n equals 1 for hydrogen. Okay, so if it does absorb energy and bumps up, that's the excited state. Its ground state is n equals 1. Okay, now as long as an electron moved in an allowed orbital or stationary state, the electron did not emit any energy. So as long as it's here in this ground state right here, it's not emitting any energy. But if you pass electricity through it, then the electron can move from one allowed orbital to another. So it's going to absorb that energy from the electricity. Okay, so it goes to an excited state. Then when it loses that energy, it drops back down to another state, and it releases that energy. Here we see in red as what's called a photon. Okay, so when it releases that energy, that's called a photon, and that is just a packet of light. Okay, and so that's where those bands came in on this previous spectra, is the hydrogen atoms were gaining energy and then dropping back down to their ground state. And as they did, they released energy in the form of light. Okay, so those are Bohr's postulates on that. And it was soon discovered that all elements, just not hydrogen, had their own what's called emission spectrum that we saw in hydrogen. Like this top one is hydrogen. Well, here's the emission spectrum for mercury. We see that it has a lot more bands and more wavelengths. And neon, here's neon. So scientists can take the light that's coming from a star and they can analyze it with these emission spectrums. And that's how they can tell what stars are made of and what planets are made of, because they match these bands up that they get from the emission spectrum to the known bands for the different elements. So that's how they know that, this star is made out of hydrogen and nickel or helium and carbon, because we know what the bands are for those and we compare it to the light that comes from these stars. So that's how it brings in chemistry for the light. The study of light is because it's the movement of electrons between orbitals that emit this energy and produce this light. So we need to look at the electromagnetic spectrum to know about the different wavelengths of different waves. The amount of energy that an electron absorbs would be equal to the amount of energy it's released when it fell back down to its ground state. And that energy would produce different wavelengths of light. And there's only a certain very small section of wavelengths that we're able to see with our eye. And it's right here. It's called visible light. This is the only part of the spectrum that we can see with our eye. And so what they've done here is they've taken this very small section and they've blown it up and expanded it out. And that's what this section right here is with the color. But it fits right into here. And you have this printout in your reference materials. We're going to be using this information to calculate energy, calculate wavelengths, and calculate frequency of light. Right? So here we have frequency. Okay, this is a very low frequency here, up to a very high frequency. And then energy. This is low energy all the way up to high energy, and these are the different waves. Radio waves are very low energy. It's the lowest energy wave that we know about. And then the next one is microwave, and then infrared, and then we have visible light. So something important that you need to remember is that red, the color red, is very low energy. And if you're an artist or you study art, then that may be contrary to what they say about the color red in art. Usually the color red in art is associated with high energy, but it's actually scientifically very low energy waves. Okay. And then we go all the way up to violet here. Okay. And then right above violet is ultraviolet, and that's UV. That's UV light, so it's short, UV, ultraviolet. And that's light that comes from the sun, and this is the wavelength that gives you the sunburns that are very painful. And then above that is X-ray, okay, and they use X-rays to, go through your body and hit a special film, and it shows density of tissues, and so your bones come out very white because your bones are dense. And so that's how they see your bones through your skin. And then gamma radiation is associated with nuclear power plants and nuclear energy. Gamma rays, very, very high energy. And these waves are so high energy and so high frequency that they can get into the cells and disrupt the DNA and cause cancers and tumors. And the wavelength here, the low wavelengths. The low energy are very long wavelengths. So there's a very big distance between the waves here. And then up here in gamma rays, the wavelength is very short. So there's a way that you can remember the colors in order. Okay, and you may have learned this in junior high, and it's red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. So it's kind of like a name, Roy G. Biv. Okay, and that's how you remember the lights of the rainbow in order. All right, so let's look at some of these calculations that we're going to be using in this section. And there's two constants for the equations that we're going to be used. And all of this is found in your reference materials in the light section. Okay, one constant with the symbol of H is called Planck's constant. And this comes from his experimentation on energy absorption and emission. The scientist's last name was Planck. And that's going to be 6.626 times 10 to the negative 34th joules seconds. And joules is, it says right here, the units for energy, okay, are represented as joules. And then the S is seconds, so this is joules seconds. These two are multiplied joules seconds. We're going to need the speed of light, and C is the variable that we use to represent the speed of light. And this is 3.0 times 10 to the 8th meters per second. So for every 1 second, this travels 3.0 times 10 to the 8th meters. Okay. All right, so the actual equations, the speed of light is equal to F, and that's going to be frequency. Okay, frequency. Okay. Sometimes you're going to see frequency represented with the Greek letter nu. It kind of looks like a weird letter V. Okay, it's the Greek letter nu. But more often than not nowadays, you just see it as F. Okay, and then this symbol here is the Greek letter lambda, and this is for wavelength. Okay, and that's the wavelength. And the way I remember that lambda is the wavelength, or that little symbol there is the wavelength, because if we look at, I'm going to go to the next slide real quick. If we look at a wave, okay, and let me change colors so you can see this. If we look at a wave like this right here, and we just look at this section of a wave, it kind of looks like this section of the letter lambda. See how it goes up and then slants and then curls up at the bottom with a little kickstand on it. So if I were to take that and put a little kickstand on it, then it looks like the letter lambda that they use to represent wavelength. So this is the wavelength is lambda. Okay, so that's the symbol for lambda. And then E is this symbol that, capital E is the symbol that's used for energy. Okay, so let me write this here, energy. Okay, and then H we see here is Planck's constant. C, again, is speed of light. And so these are the three equations that you're going to be using in this section on calculating light and energy and frequency. One conversion factor that you're going to need to know is for the prefix nano, because wavelengths, if we go back and look, oh, it's right over here. So wavelengths of visible light are measured in nanometers, in portions of a meter, nanometers. And the prefix for nano is 1 times 10 to the negative 9th. Just like the prefix for milli is 1 times 10 to the negative 3rd. Okay? So nano is another one now that we're introducing. It's 1 times 10 to the negative 9th. All right, now combinations of these equations can be used to solve problems in this section of light. So we could combine these different equations or rewrite them, algebraically rearrange them to get all the equations that we're going to use in this section on light. This section right here, and I believe this is also in your reference materials, if I'm not mistaken, tells you the different wavelengths of red light. So red light is from 620 to 780. Okay, orange is 585 to 620, etc. So you'll need to know these because there are questions that say, you calculate the wavelength and you get a numerical value for a wavelength, and then it asks you what color corresponds to that on the electromagnetic spectrum. All right, so before we go into the actual problems that we're going to be working out, the examples, I want to talk about the different parts of a wave first, because you're going to have questions on wavelength and frequency. So here we have an example of a wave that gets smaller and smaller. Wavelength is the length of a wave from two peaks, okay? Or it could be two troughs, okay? So that's called the wavelength there, okay? And that's represented again as lambda. All right, and then frequency is how many waves you have in a given section. So if we were to take this and call this a given length, a given section, how many waves happen during that section? So if we go down here and we put this section here, we see that we only have one wave that occurs in this section. So the wavelength would be 1. But if we move this down to a very, where the waves are shorter, then we have more frequent waves within this section. So that's what frequency is. How many waves do you have in a given length? So here we would have 1, 2, 3 down here in this section, where down here we only have 1. Okay, so this is high frequency, and this is low frequency waves. Okay, and long wavelengths or very short wavelengths. See, the distance between these two peaks is very short. Okay, so that's what it's talking about when we're talking about wavelength and frequency of light or any wave on the electromagnetic spectrum. All right, so here are some typical questions that you're going to see, and I've copied some of the equations over here on the right-hand side for you. Okay, these are just the equations that you're going to use for these. So this first question says, find the frequency and energy. Okay, so frequency and energy. We're going to underline that because we're going to find both of those of light corresponding to the following wavelengths. All right, so 410 nanometers is the wavelength. So I'm going to take that, I'm going to write it here. Nanometers, and that's going to be equal to wavelength. All right, so I need to find frequency. So what I'm going to do is I'm going to look at my different equations that I have and see, given the wavelength, what one I can use to find frequency. So here, energy is equal to HF. There is not a frequency. I'm sorry, there is a frequency, but there's not a wavelength in this particular equation. So I cannot find that. Okay, on this one, I cannot use that. I'm sorry. On this equation, we have wavelength, right? And we know what H is, and we know what C is, right? But energy, we can't directly or we can't easily find the frequency using this equation because there's no F there. So if we look at this one, speed of light is equal to frequency times wavelength. Well, we have the wavelength, right? And C, the speed of light, is a constant, so we have that number. So here's frequency. We can use this equation right here for us to calculate this first unknown frequency. So we're going to have to rearrange this a little. So we have C is equal to frequency times wavelength. Now we're solving for frequency. Okay, so we're solving for this one. And the one we're solving for, I like to put a square around because that tells me in my head, don't mess with that one. Don't move that one. That one's locked down. So now we're going to have to get rid of this wavelength, okay, so that frequency can be on the equal sign by itself. Well, since you're multiplying here algebraically, in order to get rid of wavelength, we're going to have to do the opposite function. So what's opposite of multiplying? That would be dividing. So I'm going to divide both sides by wavelength. Okay. And here we have wavelength over wavelength. Remember, what's on top can cancel what's on bottom. So these two now cancel, and we have frequency is equal to the speed of light divided by wavelength. So there's our formula that we need. Okay, so I'm going to go ahead and erase this so I can have room to write. All right, so we're going to be using the speed of light and wavelength. Well, we have wavelength here. So the speed of light is another one that I'm going to have to write down as my listing out my givens. So the speed of light is 3.0 times 10 to the 10 to the 8th, not negative. 3.0 times 10 to the 8th meters per 1 second. Okay, so remember, when we do meters per second, it's meters over seconds. 1 second, so it's this many meters per 1 second. Okay, so make sure you remember that. Okay, and I'm going to go back just to make sure, just to verify that this is the correct speed of light, because I don't want to make a mistake. That's what chemistry is all about, being very meticulous about checking. 3.0 times 10 to the 8th. Okay, 3.0 times 10 to the 8th meters per 1 second. All right, so the next thing you have to do is put this over frequency. So we have this now over 410.2 nanometers. All right, so the next thing that I want to point out is that we have meters here and we have nanometers here, and that doesn't work. You have to make sure that you have all of your units in the same unit. So we want to take this nanometers and convert it to meters. And I'm going very slow and meticulous on this first one, but the second example that I'll work out, I'm going to go much faster. So in order to make this work, we have to change these nanometers to meters. So I'm going to take 410.2 nanometers, okay, and put it over 1, because this is a conversion. Remember I told you we're going to use conversions all year? Well, here we go again. All right, so now I'm going to start asking myself these questions. What unit is it that I need to get rid of? The answer is nanometers. Where do I put that unit so that it can cross cancel? In the bottom. And what am I converting this to? What conversion factor can I make here? I'm trying to convert it to meters. So here we have nanometers and meters. So what did we say the equivalent was for the prefix nano? We said that is equal to 1 times 10 to the negative 9th. That's the prefix. All right, so where do I put this information for nano? It goes in front of the base unit. So I'm going to put it right here. 1 times 10 to the negative 9th meters, 1 nanometer. Okay, so cancel what you can cancel. That's the next step. Ask yourself, do I have the unit that I want for my problem or for the answer? So I'm going to end up with meters, because that's the unit that we have not canceled, and that's what I want. So I can stop here and do the math. Okay, so 410, this is where you pick up your calculators and punch buttons with me. 410.2 times, now make sure you put this in your calculator correctly, 1 EE negative 9. Okay, and you're going to get the answer is 4.102 times 10 to the negative 7th meters. Okay, so now we've converted this into meters. So instead of this, I'm going to use 4.102 times 10 to the negative 7th meters. Okay, so I'm going to take this out and you probably don't want to erase, just mark it out. And I'm going to write 4.102 times 10 to the negative 7th meters. Okay? All right, now I'm going to erase this down at the bottom so I can have room to work. And now we're going to just do the units. I want to show you how the units cancel because that's very important to understand the units. And I always do the units before I do the numbers. So here I've got meters per seconds per meters. Okay. So I'm dividing these two. Let's make this a fraction, meters over 1. So here I'm dividing two fractions. Okay. Now, if you remember from your algebra, this is why it's so important that you do well in algebra before you come to chemistry. You had algebra in the 9th grade because now we're going to start using and applying that algebra in chemistry, which you have in the 6th grade. So dividing two fractions. Okay. How do you divide two fractions? Well, if you remember keep, change, and flip, then you're going to get this right every time. So we're going to keep this fraction, so meters over seconds. We're going to change this sign right here from division to multiplication, which is the opposite. And then we're going to flip this one, 1 over meters. Okay, so now we've just simplified this. So how do you multiply two fractions? Well, we do it in dimensional analysis all the time, multiply straight across. So we have meters over seconds meters. Okay, now we're not quite finished yet. What's on top can cancel what's on bottom. So when I cancel these out, I have 1 over seconds. It's going to be my unit for this problem. Okay, so 1 over seconds is the same thing as hertz. Okay, so hertz is a unit that is represented by 1 over seconds. And this shortcut for that is H is E, hertz. Okay, so our unit we're going to have for our answer is 1 over seconds or hertz. Okay, so again, I'm going to erase all this because we just worked out our units and what our unit is going to be for frequency. Okay, and frequency is measured in hertz, right? So now I just figured out all of these units here is 1 over seconds, which is hertz. So now I just have to worry about the numbers. So we have 3.0 times 10 to the 8th divided by 4.10. Where's my calculator? Times 10 to the negative 7th. All right. So pick up your calculators and work this with me. Okay, so 3.0 EE8 divided by 4.102 EE negative 7. Okay, that's going to give us a long number. I'm going to write it here, 7.313505607 times 10 to the 14th power. All right, so how many sig figs do we need? There's 4 sig figs there, so I need 4 sig figs here. So 1, 2, 3, 4. Okay, so this 5 is going to tell us if we round or not. A 5 does bump the score up, so it's 7.314. 314 times 10 to the 14th power. Okay, so that is the frequency of the light that corresponds to the wavelength of 410.2 nanometers. All right, it tells us also that we need to calculate energy. So I'm going to erase all of this, and I'm going to keep this now. because we can use this information frequency to calculate energy right here. So H is a constant, right? So H, E, we're calculating energy. Now we know the frequency, so we can calculate energy from this. Okay, but before I do that, I want to show you something real quick. See how this says E is equal to HC over lambda? So let me rewrite that. E is equal to HC over lambda. Okay, and then we have E is also equal to HF. Well, what did we just say right here that this was? See this? The speed of light over the wavelength is the same thing as F. So we can just substitute F in right here. Okay, so these equations are really the same. So, but instead of writing C over lambda, we use frequency. Okay, and we get that from the speed of light as frequency times wavelength. All right, so E is equal to, let me erase a bunch of this. And like I said, on this next example, I know I'm taking a long time on this. I'm going very slow and meticulous so that you understand all this. I'm going to go a lot faster on the second one. All right, we're almost there. Okay. All right. So energy is equal to Planck's constant times frequency. Well, we have the frequency and we know Planck's constant, so we just need to plug those in and then calculate energy. So energy is equal to, okay, Planck's constant, 6.626 times 10 to the negative 34th joules seconds. Now I'm going to look this up just to make sure. 6.626 times 10 to the negative 34th joules seconds. 10 to the negative 34th, I didn't write my 4 there, joules seconds. All right, times my 7.314 times 10 to the 14th, 1 over seconds. Okay, it's really hertz, but remember, hertz is 1 over seconds. Okay, so let's get our units. So we have joules seconds times 1 over seconds. Okay, seconds cancels. What's on top cancels what's on bottom. So we have joules over 1. So energy is going to be in the unit joules. Okay, and if we go back in our notes and look to this page, remember I said energy here. The units for energy are joules. So there you go. We just worked it out and saw that the unit for energy is joules. So now we just have to multiply these two numbers together, and we're going to get the energy of this wave. So let's take your calculators, pick it up. 6.626 EE negative 34 times 7.314 EE 14. Okay, we're going to get, let's see, I'm going to write it here, 4.8462564 times 10 to the negative 19th joules. Okay, we need 4 sig figs. So this is 1, 2, 3, 4. So this 2 tells us whether we round. A 2 does not round it. So we get 4.846 times 10 to the negative 19th joules. Oops, I always do that. Make it look like a J. 19th joules. All right, and so that's the energy. All right, very good. Now, remember, all of the problems that you're going to see in this section are just these equations manipulated and rearranged. Okay? It could ask you to solve for, let's see, the speed of light. It could give you energy and ask you to solve for wavelength. So there's a bunch of different equations that we could get from this. Not a bunch, but a few. All right, so let's do one more like this with a different wavelength. Okay, so we're trying to get energy and frequency. Okay. All right, so remember, we used C is equal to frequency times wavelength, and we're solving for frequency. So the frequency is equal to C over lambda. Okay, so we know that we have meters here and nanometers here. So the first thing that we're going to have to do is convert those nanometers to meters. Okay, so I want to get rid of nanometers, convert it to meters. 1 times 10 to the negative 9th. Nanometers cancels. Okay, so we're going to get 4.341 times 10 to the, let me do this real quick. Okay, calculator, 434.1 times 1 EE negative 9. Oops, I did that wrong. Push the wrong button. 434.1 times 1 EE negative 9. Okay. 4.341 times 10 to the negative 7th meters. All right. So we have the speed of light, which is 3.0 times 10 to the 8th meters per second over 4.341 times 10 to the negative 7th meters. Meters cancels, leaves 1 over seconds. Okay, 1 over seconds we know is hertz. Okay, so we're going to report that in hertz. Okay, so we're going to take the speed of light. Oops. 3.0 EE8. My calculator's messing up. Hold on. Okay. 3.0 EE8 divided by 4.341 EE negative 7. Okay. That's going to give us how many sig figs? 4. 1, 2, 3, 4. 6.911 times 10 to the 14th hertz. Okay. Now we're going to calculate energy. Energy is equal to Planck's constant times frequency. So energy is equal to Planck's constant times frequency. Here we have our frequency. So Planck's constant is 6.626 times 10 to the negative 34th joules seconds times 6.911 times 10 to the 14th, 1 over seconds. Seconds cancels, leaves joules. I'll write it here. Okay, so multiply these two. 6.626 EE negative 34 times 6.911 EE 14. Okay, we're going to get, let's see, 4 sig figs, 1, 2, 3, 1, 2, 3, 4. Okay, so the 2 does not round the 9. So we're going to have 4.579 times 10 to the negative 19th joules is equal to energy. Okay? All right. So those are the calculations for this section on light. Make sure that you slap that like button right across the face. Give me a subscribe and a thumbs up. And if you leave a comment and it's a positive comment, you're not trolling me, I will post it.